I now want to discuss vertically vibrating springs. So this is simple harmonic motion, and it varies from the horizontal situation because you have it hanging by gravity. Gravity is stretching out the spring. So I'm going to attempt to do this by giving you a big summary paragraph here, and hopefully the description will be mostly adequate. And then on the next, after this, we'll take a look at an example and see how this all works out with an example problem. So, what's the difference between horizontal and vertically vibrating springs? The horizontal spring is unstretched in the equilibrium position. So you consider that as no stretch at all. But the vertical spring is stretched by an amount equal to that which is required to overcome gravity. So it's mg over k. In other words, mg is equal to k times x. So x is mg over k. Because force is kx, and that's just equal to the weight. All right, so the acceleration then at the equilibrium position is 0. By definition, at the equilibrium position, there's no restoring force. The net force is 0. And that's actually the restoring force as well. There is none. But there's still a force because the spring has got to hold up the weight of the mass. So that's why it's stretched in the equilibrium position. But that does not affect the period of vibration. So it doesn't matter how much a spring is stretched. When you oscillate it, its period remains the same. So that's perhaps a little surprising, but fundamentally, the spring that's vibrating the vertical object, the object in vertical SHM, that period is the same as if you somehow could put it on a frictionless table and make it oscillate it horizontally. So the spring must provide an upward force equal to the downward force of gravity. So in the equilibrium position, the spring force, if it was oriented horizontally, is 0, but it's not. It's oriented vertically, and so now it's equal to the weight upward, mg upward. So that's a big difference. So don't confuse spring force with net force. They're only the same thing if it's a horizontal spring. If it's a vertical spring, you have no net force at the equilibrium position, but you still have a spring force equal to mg. All right? So net force for simple harmonic motion. Net force. I'm going to call that FSHM, the simple harmonic motion force, or the restoring force, F sub SHM. That's kind of nice, isn't it? This will always be the net force trying to restore the object to its equilibrium position, and generally it's not minus kx. All right, again, that kx in the equilibrium position, which is mg, results in no net force because it's just hanging there. It's simply, this is simply overcoming gravity in that case. So the SHM force is the restoring force. We can equate it to the displacement from the equilibrium as follows. Basically, at the equilibrium, there is no SHM, F sub SHM force. But if you displace it from that position, then there is. So the simple harmonic motion force is minus k delta x equilibrium. So there's the kx idea. But at the equilibrium position, it's just delta x. How much is x stretched, the spring stretched from the equilibrium position? That's why it's delta x sub eq. All right. If that doesn't make sense, it will shortly. So for the next problem that we're going to do, we had v is 2 pi over t squared of a squared minus x squared, and also we know that the period is 2 pi squared root of m over k. And we can combine this together. You see this 2 pi over t? this has 2 pi over t. Let's divide both sides by t and solve for that as follows. 2 pi over t equals square root of k over m. That's kind of nice. Then we get v is equal to square root of k over m times square root of a squared minus x squared. And in this formulation for the speed, notice it's not dependent on a measured quantity like the period. Let's figure out what the period of oscillation is, and then we can know what the speed is based on measuring x. Now we have a mass that's known and a spring constant that's known, and all you have to do is measure x and you get the speed. So that's kind of nice. And now let's move on to an example problem using these ideas. So here's our vertical spring example problem. We have a 3 kilogram brick that's oscillating vertically, and we have it released from the unstretched spring, and it has a spring constant K of 10 newtons per meter. The conditions are that at the moment the brick is 80 centimeters or 0.8 meters down, and we are going to determine the amplitude, period, net force, spring force, and speed at that position. So notice its motion is actually on the way up. So it's moving up, but its position is down below the equilibrium position, and we start it from an unstretched position. All right, it sounds perhaps a little confusing to get all this stuff. Not so bad. So to get the amplitude of the vibration, if we start with F is equal to kx, and we recognize that the amplitude is the maximum x, I know this looks like y, but I'm calling it x, a minus a and 0. So at the maximum value, that's either this or from here to here. So from the equilibrium position to either amplitude, that's x max, and it's F over k. Because, remember, for the spring, F is equal to kx, F equals k multiplied by x, bring the k over here. But the force is the weight at the equilibrium position. So this is just 30 over 10, which is 3 meters. And we just solve for the amplitude. And there's an important point to make here. This method I just used was really solving for the amplitude position from the unstretched position. In other words, how much does the mass stretch the spring to the equilibrium position? So we set F is equal to mg. All right, so that solution gave us 3 meters, and now that's the amplitude of the vibration because it passes through the equilibrium, inertia takes it on, and it moves it just as far down below that, another 3 meters back to 0, and then all the way up to the unstretched position again. If we had started not from an unstretched spring, but from a spring stretched, say, halfway, then it would oscillate with a period. Well, the period's going to be the same, but the amplitude would be 1.5 meters instead of 3 meters like this. All right, so what we would do, though, if we started at 1.5 meters, we would still solve for this 3 meters to the equilibrium position from the unstretched. But just recognize that the mass started partway down, so the amplitude would be less. Okay, hopefully that's not too confusing. Now let's find the period. Period, 2 pi square root of m over k. Just plug and chug. We have m, we have k, and out pops 3.44 seconds. So we have now the amplitude, we have the period. Let's get the net force. The net force is the simple harmonic motion force, and it's k delta x eq. Notice I just dropped the delta because I'm lazy. I don't like to write much. So k x eq means the position x from the equilibrium position. So that makes sense as well. Well, how far are we from the equilibrium position? We are 0.8 meters. So 10 times 0.8, 8 newtons. Now how do I know it's up? I know it's up because We are below the equilibrium position. The spring force now is stronger or larger than gravitational tug pulling down. So then, and we also just know it's always being restored toward the equilibrium. So that's the direction of the net force. Now we could have realized that the spring is already stretched equal to the weight and then that much more. It's actually stretched 3 meters here. So the spring is stretched 3.8 meters. So that's actually all we really need for this now, isn't it? But what I want to do is do a free body force diagram because it lends itself to that. We got mg acting down. We have spring force acting up. And we know the spring force is more. It's accelerating upward. And so we actually have a net force or a simple harmonic force upward. So the simple harmonic motion force, the net force, is spring force minus gravity. Or this is like at the bottom of a loop in vertical circular motion, where the spring force is the support force. It has 2 jobs. It has to overcome the weight and provide all of the net force. That's the 2 jobs of the spring force. So the spring force is mg, that first job, plus the second job. We already know what the spring subharmonic motion force is. It's 8 newtons. So this is 3 times 10 plus 8 equals 38 newtons. The difference between the net force and the spring force is just mg. Now, what I had just said, let's see, the spring is already stretched 3 meters plus another 0.8 meters. So 3.8 meters times 10, the k, gives us 38. So that is the same thing. But this free body force diagram was useful to sort out the various forces involved. And now let's get the speed and we'll be done. So the speed is square root of k over m, square root of a squared minus x squared. We know all the numbers. We know the spring constant, the mass, the amplitude, the position x, and out pops. There it is. 5.3 meters per second is the speed. And that will conclude our basic summary and analysis of vertical springs. And hopefully you feel like you're somewhat equipped to solve some of these problems now.